So, welcome this Wednesday on the live conference, and we will have our first plenary speaker. Marco Abbadini from Salerno, Italy.
Exactly.
Whenever you're ready.
Okay, thank you. So thank you for being here. I would like to thank the organizers for inviting me here to talk. I feel very honored, very happy to be here. Also because my first conference was a Blast conference, was 5 years ago in Denver. So it brings me also back this nice memory I have. So thank you again. And in these 5 years, the perception of the meaning of some words changed. So now we're fully aware that a word like positive can have different meanings, like can be something good, like we're happy to have a positive review of one of our papers, but maybe not that much about having a positive viral offense. So what about a positive MV-algebra? Is that good or bad? Well, in this talk, we're going to introduce positive MV-algebras. We'll provide some initial good results for positive MV-algebras. And well, the idea is that they were introduced very soon in the past, a few years ago. And so the theory has to be developed. And now in this talk, I just provide some initial results with the hope to develop this theory. Now, what are positive MV-algebras? Well, the idea is that they are two MV-algebras, which boundary distributive lattices are Boolean algebras. Now, what are these four structures? Well, Boolean algebras are the algebraic semantics of classical propositional logics. Boundary distributive lattices are, let's say, the Boolean algebras without negation. So they capture the positive fragment or the negation-free fragment of classical propositional logic. MV-algebras, MV stands for many-valued, are the algebraic semantics of Lukasiewicz many-valued propositional logic. It's a logic, also shortened Lukasiewicz logic, where many-valued stands for the fact that instead of having two-element sets as a set of truth values, we have the whole interval 0, 1. I will spend some more words on these algebras in the next slides. And positive MV-algebras are essentially MV-algebras without negation. So they encode the positive or negation-free fragment of Lukasiewicz logic. So this research is placed in a research of positive fragments of logics that has been going on in the last 3 decades at least. For example, Dan studied positive modal logic. The corresponding algebras are positive modal algebras, and these are modal algebras without negation. Or other researchers study positive relation algebras, which are relation algebras without the complementation. And so our research sits along this trend. So, why I'm talking about positive MV-algebras? Well, Cintula and Krupa used the positive fragment of Lukasiewicz logic in game theory, essentially because the winning coalitions are monotone, meaning that if I join a winning coalition, it remains a winning coalition. So that's why the positive fragment came up in game theory. And then again, Krupa with Cabrera and Gibson defined positive MV-algebras and provided some interesting results. And then I got interested in these algebras because they allowed me to obtain a duality for certain class of topological ordered spaces introduced by Nachbin, which are equivalent to stably compact spaces. And in general, okay, another two researchers suggested that High-Sync algebras are based on bounded distributive lattices. Maybe an appropriate many-valued version of High-Sync algebras may be based on positive MV-algebra. So, say an MV intuitionistic logic may be based on these algebras called positive MV-algebras. In general, for me, these are interesting because they're very well behaved. They're also complex enough to be a good study case for some results in duality theory and general algebra. Okay, let's go more in detail about what these algebras are about. So the history starts with Lukasiewicz, which introduced this logic, which takes 0, 1 as a set of truth values. It was perfectioned also together with Tarski in the 30s. And the algebraic semantics are MV-algebras, introduced by Chang. So Chang was quite unhappy with a certain proof, and so introduced these algebraic semantics to give a shorter and simpler proof of the completeness theorem for Lukasiewicz logic with respect to the unit interval 0, 1. And in fact, before introducing MV-algebras, let's see the first main example of MV-algebra, and it's the unit interval 0, 1 with the following operations. We take this class or truncated class, which is it's similar to the usual class, but the usual class is not internal to 0, 1. It might exceed 1. So if it exceeds 1, we take 1. So this truncated class is the minimum between x plus 1 plus y and 1. So for example, 0.3 plus 0.2 is 0.5, but 0.7 plus 0.8, since the usual sum would be 1.5, we take just 1, the minimum. And we have the negation defined by 1 minus x, so not 0.3 is 0.7, and we take 0 as a constant. And this is the main example of an MV-algebra, the leading example. And MV-algebras, well, are the algebras the variety generated by 0, 1? Is the variety generated by 0, 1, but the official definition just takes a few finite list of equations. So an MV-algebra is an algebra with the signature plus not 0 that satisfies this equation. It's a commutative monoid. The negation of x is x, and x plus not 0 is not 0, and these other more complicated axioms. All these equations hold in 0, 1, and they're just a finite base for the variety generated by 0, 1. So this was a theorem by Chang. And also, this theorem was the reason why Chang introduced MV-algebras, to prove a corresponding theorem for the logic. So, in other words, MV-algebras are homomorphic images of subalgebras of powers of 0, 1. Okay. So examples are the unit interval 0, 1, any subalgebra of 0, 1. Some interesting subalgebra are the two-element set 0, 1, and here the class is equal to the maximum, the join. Or also what is denoted by L2, which takes 0, 1 half 1. This is a subalgebra, and so an MV-algebra. Any Boolean algebra is an MV-algebra. So you just take a Boolean algebra and you define class to be equal to join. Negation 0 you already have. And in fact, MV-algebras are a generalization of Boolean algebras. Boolean algebras are a subvariety of MV-algebras. And moreover, and that's maybe how you should think of MV-algebras. If I have a set X, then the set of functions from X to 0, 1 is an MV-algebra. So you define the operation pointwise. And any subalgebra of this is an MV-algebra. And in fact, as a first approximation, if you've never seen MV-algebras, invite you to think of an MV-algebra as an algebra of functions from a set X to 0, 1, closed under plus, negation, and 0. Okay. And you can define an order on an MV-algebra, and it's a lattice order. The lattice operation are term definable. It's a bounded distributive lattice, in fact. And the corresponding order on 0, 1 is the usual order, and on 0, 1 to the X, it's pointwise order. We can also term define this operation, the De Morgan dual of plus. This will be important because it's order preserving, so it will stay in the positive fragment of our MV-algebras. This operation is the Morgan dual, and on 0, 1, the interpretation is that it measures how much the sum between X and Y goes above 1. So you make the sum, X plus Y, and then you say, okay, what's the difference between X plus Y and 1? And since you have to remain in the unit interval 0, 1, you take the maximum with 0. So for example, 0.7, we say times 0.8 is 0.5. 0.3 times 0.2 is 0. We say times, I think, just because 1 is the identity element of these times. But it has nothing to do with the usual products of real numbers. Also called the strong disjunction, while plus is called strong conjunction, while plus is called strong disjunction. Okay, but MV-algebras are somehow some difficult axioms for certain aspects, and to study them, one can use some structures which are easier to understand, which are abelian lattice-ordered groups. And in fact, okay, an abelian lattice-ordered group is an abelian group with a lattice order that satisfies this compatibility between order and the sum, so translation invariance. So R is the main example, so the sum, also the set of functions from X to R is an abelian lattice-ordered group. And the connection between abelian lattice-ordered group and MV-algebra is the following. From even an abelian group and a positive element, if you take the the interval of all the elements between 0 and 1, you get an MV-algebra. The operations are defined as X truncated plus Y is X plus Y made 1. The negation of X is 1 minus X. And 0 is the identity element of G. So, for example, the MV-algebra 0, 1 is obtained from R just by taking gamma of R with the 1 as positive element. The two element set 0, 1 is an MV-algebra is obtained by taking gamma of the unit interval of Z, which is another abelian group. Okay. And this important theorem by Undici says that every MV-algebra arises in this way. So that is, if I have an MV-algebra, I know that there exists some abelian in group G and a positive element 1, such that the MV-algebra is the interval between 0 and 1 of that group. And this is very useful because abelian and groups are easier to work with than MV-algebras. Okay, that's about MV-algebras. Let's see positive MV-algebras. Now, as I said before, positive MV-algebras are meant to be to MV-algebras what bounded distributive lattices are to Boolean algebras. Now, what is the relationship between bounded distributive lattices and Boolean algebras? Okay. Well, if I take a Boolean algebra and I take a redux with respect to join means 0 and 1, I get a bounded distributive lattice. Also, I take any subalgebra of this redux, is a bounded distributive lattice. And in fact, bounded distributive lattices are precisely the subalgebras of redux of Boolean algebras with respect to this signature. So they're subredux with respect to join means 0 and 1. what's so special about joint mean 0 and 1? Well, they are order preserving, and they are all the order preserving terms, meaning that, they are order preserving means in each coordinate they are order preserving. And they are all the order preserving terms, meaning that every order preserving Boolean term is a combination of these. So in this sense, we can say that bounded distributive lattices are the positive subredux, subalgebra of redux of Boolean algebras. And so, Haber, Gibson, Krupa defined positive MV-algebras. These are the subalgebras of certain redux of MV-algebras. Redux with respect to this signature here. This plus times joint means 0 and 1. What's special about this signature here? They are order preserving in each coordinate. We leave out negation, which is not order preserving. And they are all the order preserving terms, meaning that every order preserving term of MV-algebra is generated by this. So we can say that these positive MV-algebras are the positive subreducts of MV-algebras. And this makes them the many-valued version of bounded distributive lattices. And let's see some examples. Every MV-algebra. So take the unit interval, the two-element set, as we have every bounded distributive lattice. Here, take a bounded distributive lattice and you define class as join and times as meet. So in fact, positive MV-algebras, you can think of them as a common generalization of MV-algebras and bounded distributive lattices. So as a rough idea, maybe, and positive MV-algebras enjoy the properties that are both enjoyed by MV-algebras and bounded distributive lattices, more or less. Another example, and that's probably how you should you can think of positive MV-algebras. If I have a poset x, then the set of order preserving functions from x to 0, 1 is a positive MV-algebra with point with defined operations. And I think of positive MV-algebras essentially as algebras of order preserving functions. Here you can see why we cannot take the negation, because the negation of an order preserving function might fail to be order preserving. As a further example, let's see some subredux of the MV-algebra L2 times L2. So we have L2 times L2, and any positive subreduct would be a positive MV-algebra. So here is my copy of L2, so 0, 1, half, 1. Here's my other copy of L2, 0, 1, half, 1. And I connected the two elements if I'm taking them as in the subalgebra I'm considering. So this, if I take the pairs A, B, such that A is less or equal than B, this is a positive MV-algebra. And essentially these are the order preserving functions from a poset of two elements, the two element chain to L2. Another subreduct of interest is what we can call ordinal sum. We take the function which are, we take the pairs AB, which are either 0, where either A is 0 or B is 1. And this essentially, this would be a chain of 5 elements. So I'm stacking two copies of L2, one above the other, gluing them in a common point. So these are some examples of positive MV-algebras. And let's see some better good properties of MV-algebras. First of all, an axiomatization of positive MV-algebras. We'll define them as positive subreducts, but how can we axiomatize them? Okay, so Boolean algebras, bounded distributive lattices, and MV-algebras are varieties, and that's a good thing. What about positive MV-algebras? Is this a variety? No, it's not a variety. It's not closed under homomorphic images. So I'm going to write here the bad things about positive MV-algebras. On the other side, the good thing. not a variety. Okay, but maybe, well, since there are the positive subreducts of a variety, then it's a quasi-variety. This is very, it's not deep, just follows from the definition. It's a quasi-variety. Does it have a nice generator? Well, Boolean algebras have a nice generator. They are generated by 0, 1 as a variety, but even more as a quasi-variety also. Bounded distributive lattices as well by 0, 1. And in this side, we're going to replace equivalent set with a unit interval. So MV-algebras are generated by 0, 1 as a quasi-variety. And positive MV-algebras, just because they are the positive subreducts of MV-algebras, which are generated by 0, 1, are going to be generated by 0, 1 as a quasi-variety. So let me write it. So also, this tells you that positive MV-algebras are very much like algebras of functions to 0, 1. They're subalgebras of reduced powers of 0, 1. So very much similar to algebras of functions. And what about finite axiomatization? Well, Boolean algebras have a finite axiomatization given by equations. Same for bounded distributive lattices and MV-algebras. Here we have a finite equational axiomatization because it's not a variety. So the best thing we can hope for is a finite quasi-equational axiomatization. And we have it. So let me write it here. That was not easy. Finite quasi-equation. Okay, so I see that we are already 2 versus 1. Good. And so yeah, that was not easy, but we have this result. This is a finite quasi-equational axiomatization. These are row equations, except the last one, which is a quasi-equation. The first 3 maybe are the most intuitive one. A plus 0 is a commutative monoid. A times 1 is a commutative monoid. We have a distributive lattice, and the monoid operation distribute over the lattice operations. Then we have some more complicated axioms. I'm not going to talk about them. And then we have a sort of cancellation property. Sort of cancellation property, which recalls the cancellation property of monoids. But here it's expressed as x plus z equals y plus z, and x times z equals y times z implies x equals y. But it remembers also the distributive property for lattices, which can be expressed as x joins z equals y joins z, and x meets z equals y meets z implies.
Can you say something about why 5 is not inclusion? What is that distinction, inclusion versus quasi-equation?
Okay, yes. So an equation is or identity. So it's an equation of two terms, tau 1 and tau 2. Say this one, and here I'm quantifying. So an equation has this form. An equation between two terms universally quantified, while a quasi-equation is an implication between two equations.
Oh, so yes, 4 can be expressed entirely in terms of y0, y1.
Yes, exactly. Okay, yeah. Yes, so this, yeah, I can, this is just to be ordered. If I, instead of putting x0, I put y0 plus y. It was not clear. Thank you. Okay. So let's move on. Another. So for MV-algebras, what makes them easy to deal with was that they were intervals of certain Abelian lattice-ordered groups, and we have something similar for positive MV-algebras. These are intervals, not anymore of lattice-ordered groups, because the groups have this inverse operation, which is not order preserving. But these are the intervals of certain lattice-ordered monoids. So let's see which lattice-ordered monoids can we take. So we take a cancellative, commutative, distributive L monoid, which is a commutative monoid. We keep it with a distributive lattice order. So distributivity means distributivity of the lattice order, where plus distribute over the lattice operation. And we have cancellation, the cancellation property for monoids. So some examples: every abelian group, L group, so R, Z. The set of order preserving functions from a poset X to R. And the connection with positive MV-algebras is that I take this cancellative, commutative, distributive L monoid M, and I take any positive element which is invertible. So for example, if you're taking the set of functions from X to R, you can take the constant function 1. And the set of elements between 0 and 1, this is a positive MV-algebra. Define the truncated plus as x plus y meets 1, the times as x plus y minus 1 join 0, and you see why we want to be invertible, and join meet 0 and 1 as in M. Okay. And every positive MV-algebra arises in this way. That is, there exists some cancellative, commutative, distributive L monoid M, and a positive invertible element 1, such that the positive MV-algebra is the interval between 0 and 1. So this makes them easy to work with. Actually. So for example, 0, 1 we can is the interval of R. 0, 1 half 1 is the interval of gamma of 1 half Z 1. Also, but any bounded distributive lattice is a positive MV-algebra. So, for example, the 3 elements bounded distributive lattice, it's the interval something. Here, it's a positive MV-algebra by taking plus to join times equal to meet. What is it the interval of? We take inspiration from actually dual theory. We take 2 points, the 2 element set, the 2 chain. We take the order preserving function to Z. Or in other words, you take the pairs AB, Z times Z, where A is less or equal than B. If you take the interval between 0, 0 and 1, 1, you get a 3-element algebra, which is precisely the chain of the bounded distributive lattice of 3 elements. Okay, last thing. Wait. There's some good things that I didn't write. What was it? It's intervals of L monoids. Okay, so last thing, free MV extension. We say, by definition, positive MV algebras are the positive subreducts of MV algebras. So they embed into some MV algebra. Right. But is there a canonical embedding? And yes, but this is kind of trivial. It holds by general algebraic reasons. We have a forgetful factor from MV algebras to positive MV algebras, which has a left adjoint. And so we have a universal map, free map, which is also injective by definition of positive MV-algebra essentially. But what is non-trivial is that this free map is essentially the unique possible embedding of a positive MV-algebra into an MV-algebra. What does it mean? If I have a positive MV-algebra and I embed it into two possibly different MV-algebras, then and I take the MV-algebras generated by this two embedding, then these are isomorphic. These are isomorphic over L. So in particular, if I take the images of F and G and they generate A and B as MV-algebras, A and B are isomorphic over L. And so this can be said also as follows. If I have an embedding, it's enough to notice that it's enough to verify that it's MV generating. It generates the image as MV-algebra to deduce that it has the free property, the universal property. Or in other words, I have MV-algebras A and B, and I have just a partial function from the subalgebra L to B, and this MV generates A and is closed under the positive operations. Wherever if F preserves all these positive operations, then F extends uniquely to an MV homomorphic. Okay, this is something non-trivial, meaning that it holds in certain cases and doesn't in certain other cases. For example, it doesn't hold for monoids and groups, but if you add commutativity, we have analogous properties. Also for lattice-ordered Abbadini groups and lattice-ordered commutative monoids, and that's how we actually obtain this result using the connection with monoids. Or it holds for Boolean algebras, bounded distributive lattices. It doesn't hold for positive modal algebras and modal algebras. Okay, and that's a good thing. So it's enough to prove that something is then generated to have this free extension property. So I'm going to write it here. So embedding. And be generated implies free. Or, yeah, this is equivalent to say that there's a unique possible embedding to an MV-algebra. Okay, and just let me mention that this is equivalent to the fact, for a general fact of general algebra, this is equivalent to the fact that every equation in the language of MV-algebras is equivalent for MV-algebras to a system of equations where I don't use the negation, I just use the positive fragment. So, for example, for all, given this simple equation, x equals not y, equivalent to these other system of equations where I don't use the negation, just use the positive fragment. Or, yeah, here a slightly more complicated one, I can rewrite it in a way that I don't use negation. And okay, and this is equivalent to the more right property of before. Okay, so to recap, okay, we have some bad things about positive MV-algebras. It's not a variety, but fortunately, yeah, we started bad, but we get something good. So we have that it's a quasi-variety. It's generated by 0, 1. We have a finite quasi-equation axiomatization. We have this way of representing positive MV-algebras at intervals, so well monoids, and we have this unique embeddability or embedding plus MV generated implies M3. So with this, here I've written this. So I hope this is some good news for positive MV-algebras. that possibly could allow the theory of these algebras to further develop. Okay, yeah, thank you very much for being here and for your attention.
For Marco?
Not sure that I understood your last result, but you said equations with negations in MV-algebras can be replaced by systems of equations that do not talk about negations. But does this mean that you can give an axiomatization of MV-algebras with a system of identities that do not talk about negation?
No, well, I mean, maybe, I mean, here this is subject to the axiom of MV-algebras. So if I, probably given already the axiomatization of MV-algebras, if I'm adding some equations. And also, just to clarify, here the for all is, let's say, it's quantifying the if and only if. It's not for all here and for all.
So just a follow-up question, is that if you took the standard finite axiomatization for MV-algebras,
Yes.
replaced each axiom with your finite system of negation-free, you get some finite set of identities in the language of positive MV-algebras.
Yeah.
And does the variety it defines happen to be the variety generated by your quasi-variety of positive MV-algebras, or you don't?
Oh.
And actually, I was really wondering if the variety generated by the good quasi-variety, if you know if it happened to be finally based.
The variety generated by
The quasi-variety of it.
I conjecture it's not finitely generated. Okay. Also, because there is a similar result for L monoid, where the variety generated by R, by the L monoid R, is not finitely based. So, but if we remove this last axiom, we get a variety. It's not the variety generated by 0, 1, but still it's an interesting variety because these are the intervals of the commutative distributive L monoids without cancellability. So it's still, you get an interesting variety. We called it MV monoidal algebras, this without cancellation. I think.
Yeah. And the lattice of subvarieties of MV-algebras is well known. And so my question is whether you looked at the corresponding lattice of quasi-varieties or subvarieties of this quasi-variety, and whether this is similarly easy to calculate.
I didn't look at it. So your suggestion is to look at the lattice of, what happens if I add other quasi-equations or other equations? Okay. Yeah, interesting. I didn't. Thank you.
Which is compound. Correspondence is Victoria.
Yes.
What about yours?
Yeah, also, we have an equivalence. We have an equivalence between positive MV-algebras and homomorphisms and those cancellative commutative distributive L monoids equipped with a strong unit. So a positive invertible element which further satisfies the fact that for all x there exists n such that if I'm adding y n times, I get above x. If I'm adding y times. Yeah, we have a. Okay.
What if you go further and take the subreduct without the lattice operations?
Yes.
But you keep the order.
Okay.
I'm interested in that setting.
Yeah, that's interesting. I mean, do you have a specific question about?
Yes. The question is, I mean, your axiomatization uses join.
Yes.
And so I would just leave out those equations because the quasi-identity doesn't. And study that particular variety. It's the variety that, I mean, the quasi-variety that we're interested in.
So just to understand, so you consider the subreducts of MV-algebras, but without taking join and meet. Okay, and you keep the order.
Yes.
Okay. What is the axiomatization?
One,
yeah.
part of 4 and 5.
Oh, you say that it's one part of 4 and 5.
Yes.
You know that?
No, I don't
It's
know anything here. This is just the axioms that we make.
Okay, yeah. Yeah, I think it's a very natural question. It's very natural to consider this. Yeah, we should think more about this. Thank you. Another question?
Do you have an easy example of a positive MV-algebra whose homomorphic image is not positive?
Yes. So this was given by Gibson, Colorado, and Kuhlmann. And okay, an example of an MV-algebra. I don't know if you're familiar with the Chang algebra, which essentially has 0, 1, epsilon, 2 epsilon, 1 minus epsilon, 2 minus epsilon, and so on. We have this infinitesimal here, this other 1 minus infinitesimals. This is an MV-algebra. If I remove, now I take the reduct and I remove this, I have a subreduct, positive subreduct. And now we have a positive MV-algebra which has 0, 1, and various and infinitesimals. Now if you collapse all the infinitesimals, you get a 3-element algebra, which is a homomorphic image, but it's not subreduct.
Not so easy example.
Yeah.
Question? Still have time. More questions if you wish. Well, there are no more questions. Let's thank Marco again. And we have a coffee break, 35 minutes for a coffee break. We will return at 10:20.
Thank you.